Welcome everybody. I hope everybody is comfortable here. Yes, my talk is when and why did physicists start bashing philosophy? And the reason why I'm giving this talk is physics, fundamental physics, is in the midst of a serious crisis. If you walk around with open eyes, you see the symptoms here at the conference. And the reason for this crisis is that physicists indeed are bashing and dismissing philosophy. When I was a student in my first years, I remember that phrase, oh, that's not physics, that's philosophy. No, physics is part of philosophy. And I think many people have rightly diagnosed this crisis of physics. Lee Smolin, in his work, The Trouble with Physics, said that the work of Einstein, Bohr, Heisenberg, Schrödinger arose from the deep thought on the most basic questions surrounding space, time, and matter, and they saw what they did as part of a broader philosophical tradition in which they were at home. Now, it's clear that people like Erwin Schrödinger, all their considerations started from Greek philosophy. He wrote a wonderful little book on that. People like Einstein, their entire life pondered over natural philosophical questions such as the origin of natural constants. And also the work of Dirac, might not consider him a philosopher in the first place, but questioning these basics of natural constants and trying to unify the very smallest in the laws of the entire cosmos was, in essence, a philosophical approach. Now, where we are today, the watershed event, of course, is World War II and the atomic bomb. And after World War II, very naturally, the builders of the bomb, here we have B.T. Oppenheimer, Lawrence and Fermi, they were considered the smartest guys, the brightest minds, the leading theoretical physicists. Now, wait a minute. Intellectually, they were still very inferior to Einstein, Schrödinger, Bohr, or Dirac. There is no question about that. But these were kind of the older generation of the very successful years of theoretical physics in the first half of the 20th century. They were treated, a little bit dismissed. Bohr, you might say, well, you can criticize something how Bohr tackled the problems of wave-particle duality and so on. But at the very end, it was a philosophical question which is not solved to this day. And Schrödinger was in Ireland and did very interesting things about cosmology. Einstein was in Princeton. He was cherished as the great physicist, but not really appreciated. The so-called leading theoretical physicists of the time, they did not really appreciate the way he was doing in considering physics. And Dirac was in Florida. He had very interesting thoughts about cosmology and natural constants, but nobody cared about in post-war physics. You see this also, the famous 1927 Solvay conference where the leading physicists were discussing the basic problems of quantum mechanics of space and time. And not only suit and ties changed, the conference that restarted theoretical physics after World War II was the Shelter Island Conference, in which quantum electrodynamics started. So the deeper reason behind all this, as I have argued in last year's talk, is a difference in culture of how science is done, of how science is performed. In Europe, you have fundamental questions addressed. In America, dominated applications and technology. People were formally trying to understand, to really understand, going to the origin of the questions, whereas in modern theories we have a descriptive approach. And philosophy is a basis of the European tradition. Usefulness is American tradition. You have mostly individual thinkers that caused the revolution, and characteristic of modern science is large communities. You have Gedanken experiments that predominated in Europe, big science that after World War II started in America. Also the way how people were approaching, I think there is more humbleness and skepticism in the traditional European approach, and optimism and great visions, also in theory, in the post-war tradition. You have simple theories on the one hand and model fitting, and you have truth-seeking versus Nobel Prizes. I also like this. That's the difference. And I try today, I give you two key examples, Mach's principle versus quantum electrodynamics, which I think characterize not so much, I'm not talking so much about the content, I'm talking about the way physics is done, how problems are addressed. And I remember people saying about Mach's principle, oh, this is philosophical stuff from old Europe, don't care about, we don't need that, we are modern. And on the other hand, you hear quantum electrodynamics is the most precisely tested of all modern theories, it's fun. Now wait a second, yeah? It starts from the very name, it's propaganda. Quantum electrodynamics is not what it's supposed to be, a unification of quantum theory and electrodynamics. If it were, it would calculate, you would calculate the fine structure constant. And at the very beginning, we talk about that. It's very questionable. So I want to present these two theories, these two approaches. Mach's principle is something very profound. You might remember that Newton just postulated absolute space and time without justifying, and Mach in his 1883 work very profoundly challenged this point of view with this Gedanken experiment of the rotating vessel. And Mach said, Newton's experiment that does not tell you about absolute space. It just tells you that, well, the water in a rotating vessel is climbing up the walls, but that might be an effect of distant masses in the universe. And I think that's very, very profound and not resolved to this day. Putting forward the idea that the distant masses in the universe are responsible for inertia and also for gravity, Mach anticipated the equivalence principle. So it was very important also for Einstein, in this sense a precursor of Einstein. And keep in mind, the problem has not solved yet. Nobody knows about the origin of the gravitational constant. I like this beautiful cartoon. There's Newton in the middle of the vessel postulating unaccelerated absolute space, and Einstein pushed to the wall by centrifugal forces, struggling with the calculations of general relativity, and out there in the universe lurks the soul of Ernst Mach. And, well, I mean, there is a coincidence I should mention here. The coincidence is that the gravitational constant is related to the speed of light and the mass and the distances in the universe, and this is a very profound coincidence, and it's glossed over, it's digested, so to speak, in modern theories by this absurd multi-parameter adjustable absurdity of cosmic inflation that glosses over, devoid of any fundamental thought, but glosses over the problem. And what nobody talks about is that Erwin Schrödinger already in 1925 suggested that there is a fundamental link between the strength of the gravitational constants and these data of the universe. I have made a couple of videos on that, and you might say, okay, it's a little bit my pet theory, this Mach's principle, but if you agree or not, at the very end, you have to explain things like the gravitational constant. Otherwise, you're just believing in a god of modernity called 6.67. Where does that number come from? If we are doing fundamental physics, we have to explain things like that. Now, on the other hand, we have a theory of quantum electrodynamics, this so-called most precise unification of quantum theory and electrodynamics. And it starts, the very beginning is a fudge factor. Yeah? Look up that paper by Hans Bethe in 1947. He introduces a number which is justified by nobody, just introduced to match the data. Okay? And we have to be grateful to Oliver Conza. He's a Spanish researcher, and he did a fantastic historical study in which he demonstrates how experimenters and experimentalists, vice versa, fudged and tinkering their theories and their data to get together. I mean, there is historical proof that this is not the correct way of doing science. There were people, these were two assistants of Einstein, Corpus and Kroll, they cheated and nobody talks about. Okay? They even admitted it, but people are glossing over. So there are so many flaws in this at the very basis of quantum electrodynamics, not the least to mention Dyson's proof that the entire mathematical approach does not make sense, it does not converge. So how do you do science with mathematics that by construction does not work? It just introduces throat-lack of freely adjustable parameters in form of these coefficients that you can attach to various Feynman's graph, which are not even defined and not even published how properly these are to be calculated. All this is in Oliver Conza's papers. And of course, all this business of renormalization glosses over the fundamental contradiction that you have an electric field density, and if you integrate the energy of this field density, you just get infinity. That's nonsense. And I like the quote by Paul Dirac, this is just not sensible mathematics. Sensible mathematics involves neglecting a quantity when it turns out to be small, not neglecting it just because it's infinitely great and you don't want it. So to summarize, Mach's principle is, at the beginning there is the question, why is that? And QED is just, how do we fix that? It's an unfinished truth, I guess, and QED is established but bogus. We must tackle the fundamental question, not glossing over the contradictions. And again, you see the characteristics of European and American scientific culture. I am also mentioned QED because I like Feynman. He is such a sympathetic and likable guy and so frank and so funny. But if you really look up what he contributed to fundamental science, it turns out that sometimes it's just superficial. Look up this statement about inertia. He explains why inertia is such a riddle, and he does not mention Ernst Mach. That's just a lack of erudition and education, sorry. And then he comes up with statements like, we have to take nature as it is, don't worry about the fundamentals. No, as a theoretical physicist, it's your damn job to think about why it is, okay? We just cannot just grab data and play around. We have to ask the fundamental questions. And of course, Feynman is by far, it's not the worst guy. I mean, Gell-Mann is maybe even more arrogant sometimes, and his quotes are even more bogus than quantum electrodynamics. By the way, I can always back my claims here. Read this book of Andrew Pickering about the history of quarks, and you will see this also consists of glossing over fundamental questions, introducing free parameters and describing physics without proper thinking. Regarding the standard model, you have also the conflict between the eminent philosopher Thomas Kuhn with his landmark books, The Structure of Scientific Revolutions, and the model tinkering Steven Weinberg, who attacks Kuhn for being a philosopher and not a physicist. No, I mean, if you truly understand Kuhn's book, it turns out that the Standard Model is indeed something like epicycles criticized by Kuhn. And yeah, I also hate to say it, but the post-war scientific culture also consists in the fact that lying and cheating is okay as long as it's successful. And of course, this is not about nationality, I repeat, this is about scientific culture, and of course Europeans adapted very well. When people like Rubia, cheated for obtaining something, and if you don't believe it, read this book by Gary Taubes, with in detail describes what happens. I think this is a scandal that we need to historically work on. And to get to the core message of this talk, I think philosophy is the honest search for the truth by thinking, but we need all three components: thinking, calculating, and observations. And what we observe today is calculations without thinking, supersymmetric theories, string theories, superstring theories, 26 dimensions, and but nobody asks fundamental questions about space, time, and matter. An excellent book which also criticizes this approach is Sabinus Hossenfelder, Lost in Math. You cannot lie with math, but it greatly aids obfuscation. I think that's a philosophical text in this sense. What we also observe is experiments and data without thinking. Of course, the Large Hadron Collider is a key example. And we have given up the idea that we must understand science. We're just collecting data, trying to, well, somehow economically describe these data, but there is a real lack of not only understanding, but also the will to understand these things. And the result is a multi-parameter enterprise such as the Standard Model with its, I don't know how many parameters, other people like to count it, but if you consider the masses of elementary particles, it's more than 103 parameters. How absurd is that? Okay, these guys are defending themselves and say, no, masses are not fundamental. Why not? I mean, nature provides us with these mass ratios. Why is the proton 1,836 times heavier than the electron? Nobody knows. But these questions need to be addressed. If you're a theoretical physicist, I repeat myself, it's your job to think about and eventually to calculate it. It might be difficult. Many people tried it. Dirac tried all his life to calculate this number. Well, he did not succeed. But is that a reason that we can gloss over the problem or sweep it under the carpet? No. I mean, at least honestly admit that you have failed in this respect, as other people have done, like Wolfgang Pauli in his 1945 lecture. There's no question that there is also bad philosophy. If you're just thinking and circling around your thoughts, you probably don't get anywhere. But physics, in essence, is part of philosophy, and the reason why, physics is so successful is the introduction of the experimental method. You can separate the wheat from the chaff by, of course, Popper, by falsifiability, by doing experiments. But still, physics is a very successful sub-enterprise of philosophy. And the current problems, I think, arise from the fact that physics is bidding goodbye to this elementary principle, and thus my appeal is, if you're a philosopher, don't see yourself as a garnishment or appendix to physics. No, we should actively ask to returning this important role, the fundamental question, to physical research, and that's what we need to do. in other words, with a philosopher like Wittgenstein, we need a philosopher with balls. So, if you like more of these ideas, this is my YouTube channel, Real Physics. This is a paper addressing fundamental philosophical questions such as the origin of fundamental constants. This is my book, Bankrupting Physics, which is a translation of this Urknall zum Durchknall, which got the Science Book of the Year award. And I try to address fundamental questions of space, time, and matter in this mathematical reality. And this is my last book, Einstein's Albtraum, about the differences in scientific culture in Europe and America. Now there is the English translation. You might ask why there is an English translation, why I'm giving this talk in English. And this might be also part of the problem, because we are all here part of the American Empire, and you might even ask how long will it last. So this is the Russian translation. I think what we need is intercultural dialogue rather than heading for World War III, because world wars, as I try to have demonstrated, are not good for physics either. Thank you for your patience, and questions are welcome.
Questions? Simon?
Well, thank you for your interesting talk. But, you don't mention the problem of measurement. And I just wonder, is it just an oversight, or do you see it as irrelevant to the situation?
No. I mean, I have just 30 minutes, okay? This is the basic reason. And Feynman was one of these guys who explicitly criticized this, that's philosophy. Let's worry about that. And that's what I call the arrogance of modern physics towards these fundamental questions, of course, one of which is the measurement problem. Whether it's the correct formulation, or you might phrase it in another way, or if the problem is ill-posed, these are things I also discuss in my book, but the problem is there. We agree on that.
And may I just follow up to say, if quantum theory is indeed the most general theory, almost a framework for physical theories, if physicists themselves find themselves unable to explain it or understand it, you might think there's some sort of mental trauma going on there.
Some sort of
mental trauma going on there. Not easy that your fundamental subject in physics is something you have no idea how to explain or articulate or interpret.
Yeah, I think there is a very much even recent paper in Nature. Physicists unable to understand the consequences of quantum theory. I don't remember the exact title. But yes, I just can agree that these fundamental questions are unsolved. But, my personal take would be that this is a consequence of that we don't have understood very well the basics, which is space and time. And I would ask at this point if it's really justified this, what Minkowski introduced in 1908, that we use space and time as this stage of physical reality. That might be a problem. Yeah. Those other two questions?
Yeah, I've seen. Yeah, you go ahead.
I have a question. Can you tell me, in your opinion, what is the difference between physics and philosophy? Because you mentioned both of these words all the time without explaining them, of course. But when you go, can you go back to the slide where you compared the proton radius and the electron radius, which is some constant?
Yeah.
And you explained, someone should explain why these numbers are in the way like they are. But what happens if I figured out an explanation for this? Who prevents someone from asking the same question again, asking, why is this explanation in such a way? Why cannot ask perpetually why in this case? And that's the problem. We are not doing philosophy, we are doing physics. I guess calculation and a certain prediction is justified by just the success of it, not but just by the raw beautifulness or logic behind it. That's one of the reasons why
I think I agree with
we
this.
can introduce a certain number. As long as it works, I guess it's justified, right?
Okay, I think there are a couple of aspects. Let me, hope I can remember everything. So, first of all, you asked me about the difference, what I think the difference is between physics and philosophy. Well, I'm not sure I'm giving a proper definition of philosophy in front of an audience full of philosophers. It's very dangerous, maybe. I would call it the honest search for truth by thinking. Okay, so that tradition that started in ancient Greece with Thales von Milet and Democritus and Leucippus and so on. So what makes the difference and what has made physics successful is indeed the experimental method. You have not only your thoughts, which might be influenced by beauty or whatever, but you have to check them, to compare them with reality. And this reality check, backed by Popper's falsification, I think this is what distinguishes physics from philosophy. And that's the reason why it's so successful. Okay? This is one part. And then you mentioned problems like it's actually not the radius. This is also an interesting issue about the proton radius recently, but it's about the mass difference between electron and proton, a problem Dirac pondered all over his life. And these are unsolved questions. And of course you might object and say, okay, so many smart people have, without success, attempted to solve this, we're not successful. And okay, but we still should not forget these problems. And regarding your remark that sometimes we can insert a number and say it works, okay? Historically, what comes to my mind is Johann Jakob Balmer, who investigated in 1885, he investigated the hydrogen spectrum and said, okay, wow, there is a mathematical law behind, and I insert, so to speak, Rydberg's constant. He did not justify that at the point, but it was okay, it was fine that he set up this number and said this number somehow is woven into atomic physics. But keep in mind, later Niels Bohr explained that Rydberg constant by other constants of nature. And that's how fundamental progress always works in physics. You explain something that has not been explained yet and reduce the number of arbitrary constants you have put before in the theory. And my message is today's state of physics with dozens or 50 free parameters is a far cry from anything fundamental.
We have time for one more question.
Maybe my answer should be shorter, yeah.
It's more of a comment really, and I don't want to argue, but as a physicist, I have to answer your title question, and that's after and because of this talk.
You want to talk to me after?
No. To address your title question, when and why did physicists start bashing philosophy? It's after and because of this talk.
Okay. So, another question.
That was fast. One more power then.
Well, let me say a few words. I'm a philosopher of physics, and so I really don't want to criticize your plea for philosophy. But let me say, give you two remarks. So the first thing is, in favor of what the physicists do, one really has to acknowledge that these fundamental questions are really hard to solve. And I can understand that a PhD student in philosophy doesn't want to solve the problem of gravity or the paradoxes of quantum theory, but he wants to get his PhD written, right? And I also can understand that physicists after the war started to solve three problems, so what Thomas Kuhn calls normal science, right? They don't tackle the fundamental questions. So I can understand that, and one should, to be fair, one should say that. On the other hand, I'm a philosopher and I like fundamental questions. And we just have, and what I don't like so much in your talk is the opposition of the two. We've just had a wonderful workshop on philosophy of physics, so around the corner in another room the last days. And what I want you to say is, I know that in the last day there were much fewer audience. So most of you probably are not philosophers. And what I want you to give us an idea that, so what doesn't come out in your talk, that there is a very lively debate in the foundations of physics and in the philosophy of physics. And the two, the foundations and philosophy, they are kind of on a continuum, right? So on the one hand, the foundations, they are more mathematically oriented, there's calculations, but towards foundational questions, and philosophy of physics is a bit more on the qualitative side, and they form a continuum, and often you cannot say whether a paper is more on this or on that side, maybe it's in the middle, right? And for all who are interested in fundamental questions, the good news is there is a debate. Look at the literature. There are debates, there are papers, and there are philosophers of physics. So watch out if you're interested in these questions, and don't talk too much about the question because they're very good conversation.
Yeah, thank you for that question, comment, part of which I can agree. Let's just say that you're talking, I mean, first of all, you're correct that these problems are really, really hard. And nobody is to blame that it was too difficult. And that's why I described the pre-war physics ran into a crisis. Not by default of anyone else, but probably because it was difficult. And you're raising the question that how should a modern PhD student then do science? I mean, yeah, the truth is that true fundamental breakthroughs, they have never been achieved by someone who was under the supervision of a PhD or diploma or whatever, okay? If you look at the history of science, there was an uneducated book maker, Michael Faraday, who made the revolution. And André Marie Ampère, with people without formal education even, who made the breakthroughs. So what we have, certainly, in modern science is also an institutional problem. Institutional science in which people are under supervision, investigating problems which are considered fashionable, are probably not real science that will lead to breakthroughs, but normal science in the sense of Thomas Kuhn. And yes, this is the first thing. And the second thing is you're referring to the lively debates. Well, I would invite people to look at history. And I think there is good reason to look in a unified manner at history and philosophy of physics, because I think the major part of the debate is still superficial, focused on irrelevant or probably ill-posed topics which are fashionable at the moment, like things like Daniel Kahneman described as an illusion of the present. We try to focus on what is before our eyes, but we tend to sweep under the rug the very important things. And I'm grateful to people who constantly remind us, like this gentleman, about the measurement problem. But I think a big part of the real unsolved fundamental questions of 1930, for instance, are still not discussed sufficiently. Okay?
Thank you. Let's thank our speaker again.